Ever felt like your eyes just can't keep up? Like trying to see the individual blades of a fan spinning at top speed?
Uh-huh.
That feeling of visual information blurring because it's happening too fast. Well, that's a core challenge for equipping autonomous vehicles with robust vision, especially when things get dynamic and happen in a blink.
That's a great analogy.
Yeah,
Yeah. Traditional cameras work by taking snapshots, right? Like freezing moments in time with a set frequency.
right.
But if something important happens between those snapshots, that information is simply lost.
Gone.
Imagine trying to understand a fast-paced action sequence by only seeing every few frames. You'd miss crucial details, wouldn't you?
Absolutely. So, today on the deep dive, we're diving deep into a really intriguing alternative event based neuromorphic vision sensors.
Hmm.
The material we've got explores this bio inspired technology, its potential to, well, maybe revolutionize how self driving cars see the world, and the unique advantages it brings compared to conventional cameras.
Yeah, it's a fascinating area.
So, our mission today is to unpack exactly how these event cameras function, what makes them so promising for automotive applications, and how they're currently being developed and implemented.
Okay, let's unpack this. What's the most fundamental difference we need to wrap our heads around?
Okay, so the key difference lies in how they capture visual information. Standard cameras grab entire scenes as static frames, at a fixed rate.
Like 30 frames per second or 60,
Yes,
something like that?
exactly. But event cameras, drawing inspiration from the biological retina, operate on a completely different principle.
Okay.
Instead of taking these full scene snapshots, they record changes in brightness at each individual pixel, and they do this asynchronously.
Asynchronously, meaning not all at once.
Precisely. Each pixel independently reports a change the very instant it occurs.
So it's not about a synchronized shutter clicking multiple times per second. It's about each tiny light sensor saying, hey, the light here just got brighter, or whoa, it just dimmed, and it sends out that signal immediately. That's exactly it. These individual changes, which we call events, are the fundamental data that the sensor captures.
Okay.
And this event-driven method leads to some really remarkable benefits. For one, energy consumption is significantly lower.
Ah, because it's not processing everything all the time.
Right. Only
Oh.
the pixels that have changed. We also see incredibly low latency. We're talking in the order of microseconds
Microseconds. Wow.
because there's no waiting for the next full frame to be acquired. Furthermore, they boast a much wider dynamic range, around 120 decibels.
120 dBs, so they can see in really bright light and deep shadows at the same time.
Exactly. Perceive details in both intensely bright and very dark areas simultaneously, and the temporal resolution. It's exceptionally high because you're capturing events the moment they happen, not tied to a fixed frame rate.
Okay, here's where it gets really interesting for me. So, in a situation where a traditional camera might just see a blur due to fast movement, like a pedestrian suddenly stepping into the road,
Hmm.
an event camera could potentially provide a much more precise and instantaneous record of that
So
motion.
that's a crucial advantage, yes.
Mm-hmm.
In those demanding situations for autonomous vehicles, high-speed highway driving, scenarios requiring split-second reaction times for motion control, and applications with strict power limitations,
Right.
event cameras offer a compelling alternative visual sensing system where traditional frame-based cameras might struggle with motion blur or lack the necessary temporal precision.
You mentioned that event cameras are inspired by the biological retina. How closely do they actually mimic our eyes?
Well, the biological inspiration is quite direct.
Yeah.
In our retinas, you have photoreceptor cells that convert incoming light into electrical signals.
Okay.
And importantly, there are two main types of bipolar cells, on-end bipolar cells and OFF bipolar cells.
On and OF
Right.
error.
The on-end cells become more active when they detect an increase in light, while the OFF cells respond to a decrease. So when light brightens, the firing rate of on-end cells goes up and OF cells become quieter. The opposite happens when light dims.
Okay, I think I'm tracking now. So the on events and off events that an event camera captures are essentially doing the same thing as these on and off bipolar cells in our eyes.
Exactly. An event camera records increases in light intensity as on events and decreases as ROF events.
Got it.
And just like in our retinas, where in the absence of a significant change in light, both on and ROF cells produce very few random signals, kind of like background noise.
Right.
Event cameras also have a very sparse output when the scene is mostly static. This inherent efficiency at the fundamental level is a significant part of what makes them so appealing.
Sparse output, so less data when nothing much is happening. That makes sense. So we're getting these continuous asynchronous streams of individual events. How is this data actually structured and processed? It's not like a conventional image with rows and columns of color values, is it?
You're right, it's quite different. An individual event isn't a pixel value within a frame. Instead, it's typically represented as a tuple containing four key pieces of information. X, Y, T, P.
Okay, X, Y, T, P.
Yeah. X and Y are the spatial coordinates of the pixel, where the brightness change occurred. T is the timestamp of that event, often recorded with microsecond precision.
Microsecond again.
And P is the polarity indicating whether the change was an increase, ON, often +1, or a decrease, OFF, often -1, in light intensity.
Okay.
These events are frequently communicated using a protocol called address event representation, or AER.
AER.
With AER, when a pixel detects a change, it doesn't transmit the entire pixel's information. Instead, it sends its address, its location on the sensor, along with the time-coded details of the event across a shared digital communication line. It's a much more bandwidth-efficient approach than sending full frames constantly.
That sounds far more efficient than constantly transmitting data for every single pixel. Makes
Yeah.
sense. But how do you actually make sense of this rapid-fire stream of individual events? It sounds like a blizzard of data points.
Yeah, it can seem that way. There are various methods to transform these asynchronous event streams into more structured representations that can be used for analysis. One category is spatial encoding.
Spatial encoding.
Okay. These techniques essentially take a slice of time or a fixed number of events and project them onto a spatial grid, much like a regular image frame.
Ah, okay. Kind of creating a pseudo frame.
Sort of, yes.
Hmm.
For example, you might have constant time frames that accumulate all the events within a specific time window, say 30 milliseconds, or constant count frames that consider, like, the last 500 events triggered.
Okay.
The value of each pixel in these resulting frames might then represent the polarity of the last event there, or maybe the total count of positive and negative events within that window.
Doesn't that lose some of the timing information? The whole point was the microsecond precision.
That's the drawback, exactly. These spatial encoding methods can lose some of the very fine-grained temporal information that's inherent in the original event stream. You're trading temporal detail for more familiar spatial format.
Okay, so in those cases, we're trading off some of that high temporal resolution for a more image-like format. What are the alternative approaches, the ones that try to preserve that rich temporal information?
Right, so these fall under the umbrella of spatial temporal encoding. One example is the spatial temporal correlation filter.
Okay.
This basically attempts to filter out noise by checking if a newly detected event is close in both its location and its timestamp to previously recorded events.
Yeah.
If it's sort of an outlier in space or time, it might be classified as noise.
Makes sense. Cleaning up the data stream.
Exactly. Another really powerful concept is the time surface.
Time surface, what's that?
Imagine each pixel keeping track of the timestamp of the most recent event of a particular polarity, like the last on-end event that occurred in its immediate neighborhood.
Okay.
This creates a kind of surface, or map, that evolves over time. And the way this surface changes, its shape and dynamics, can provide valuable information about motion and temporal context within the scene.
Ah, I see. Like a heat map showing recent activity.
Kind of like that, yeah. A temporal heat map.
Mhm.
It's been successfully used for tasks like object recognition and tracking.
That's a really interesting way to visualize it. What other techniques fall into this spatial temporal category?
Well, we also have the leaky integrate and fire, or LIF, neuron model.
LIF neuron. Sounds very bio-inspired again.
It is. It's a computational model inspired by how biological neurons work. In this context, each incoming event effectively adds a little bit to the neuron's membrane potential, let's call it.
Okay. Like charging it up.
Sort of.
Wow.
And when that potential reaches a certain threshold, the neuron fires, generating an output spike. This acts as a way to process the temporal sequence of events.
I see.
And it's a fundamental building block for spiking neural networks, or SNNs, which are specifically designed to work directly with this type of event-based data.
Yes, and ants. Okay, that's a whole other topic, but good to know.
Any others?
Yeah, there's the voxel grid approach. This divides the temporal dimension into discrete bins, like little time slices, and represents events as three-dimensional voxels. So you keep both the spatial XY and the temporal T distribution.
So like a 3D grid of event activity over time. Exactly. And finally, there's something called the Event Spike Tensor, or EST. This is a more recent approach, kind of learning-based. Measurements are associated with individual events, and then a learnable filter, or kernel, is applied to extract meaningful signals. The idea is to let the network learn the best way to represent the event stream for a given task.
Interesting. So letting the AI figure out the representation.
Pretty much. And
Hmm.
naturally, alongside these representation methods, there are also very specific techniques developed just to identify and reduce noise within the raw event data itself. You always have some noise to deal with.
Right, of course. So we've got these incredibly efficient sensors generating this very different kind of visual data and ways to process it. How are they actually being used in the very real and demanding applications of autonomous driving?
Ah, the applications. Yes, they're quite diverse and really play to the unique strengths of event cameras. For instance, in object tracking.
Like following pedestrians or other cars?
It's exactly. Clustering algorithms like Gaussian mixture models can be directly applied to the sparse event data to achieve robust tracking, especially for things like pedestrians, even in challenging lighting or weather conditions where they might be hard to see otherwise.
Okay. And detection, just spotting objects in the first place.
Yes, for object detection, researchers are leveraging both traditional convolutional neural networks, CNNs, which usually work on images,
Right.
and those bio-inspired spiking neural networks, the SNNs we mentioned. Because event cameras excel in situations with difficult lighting, high dynamic range, and rapid motion.
Yeah.
They can provide high-speed object detection even when the autonomous vehicle itself is moving quickly.
That seems critical, detecting things while you're also moving fast.
Absolutely.
Yeah.
And interestingly, in some cases, pseudo-labels generated by traditional frame-based CNNs running on regular camera data
Hmm.
are used to help train the event-based networks.
Ah, so using the answers from one sensor to teach the other one.
Kinda, yeah. It's a way to bootstrap the training process for the event-based systems using insights from more established methods.
That's a smart way to leverage existing technology while pushing the boundaries of the new. What other driving-related functionalities are seeing benefits from event cameras? The sources mentioned a few others.
They did. Our sources highlight several other promising areas. Semantic segmentation.
That's understanding what everything in the scene is, right? Road, car, sky.
Exactly. Assigning a label to every pixel. Also, steering prediction and lane extraction are all applications where event cameras are showing significant potential.
Lane extraction sounds really important, especially in tricky lighting.
Definitely. And for lane extraction specifically, there's a dedicated high-resolution event-based dataset called DET. It focuses on challenging lighting conditions, often found on roads, like inside tunnels, under bridges, complex urban areas.
Places where regular cameras might struggle with sudden brightness changes.
Precisely. Event cameras are also proving valuable for estimating optical flow, that's the apparent motion of objects in the scene,
Okay.
and for depth estimation. Sometimes, even in an unsupervised manner, meaning without needing tons of manually labeled training data, which is a big plus.
Unsupervised learning is always attractive. Less data labeling effort.
It is. And if you want to leverage the vast library of existing computer vision algorithms that work on images,
Yeah.
you can even reconstruct high dynamic range, HDR, intensity images
Hmm.
from the event streams. So you get an image out, but one that benefits from the event camera's capabilities.
Wow, so you can get the best of both worlds sometimes.
Potentially, yes. There's also ongoing work on panoramic stereo vision using event cameras, and even for monitoring the driver's state.
Driver monitoring, like for drowsiness.
Exactly.
Yeah.
Detecting signs of drowsiness by analyzing subtle eye and mouth movements, which event cameras can pick up very quickly due to their temporal resolution.
Figure 1 in our sources actually gives a really nice visual overview of many of these applications. Right, I saw that. It really does sound like a versatile sensor for autonomous perception. But, to fuel all this research and development, you need vast amounts of relevant data, right? What kind of event-based data sets are specifically available for autonomous driving research?
Absolutely. The availability of high-quality data sets is critical. We've already mentioned the DET dataset for lane extraction.
Right.
There's also NCARS, which focuses on recording vehicles in complex urban environments using a dynamic vision sensor, one type of event camera.
Okay.
The MVSEC dataset is particularly valuable. It provides synchronized data from stereo event cameras, so two cameras, for depth perception, along with ground truth information from LiDAR sensors.
Ah, so you can compare the event camera data with LiDAR. That's useful.
Very useful. It makes it ideal for 3D perception tasks like visual odometry, estimating the vehicle's motion and obstacle avoidance in various driving conditions.
I got it.
And then there's DDD-17. This is a large-scale dataset recorded with a Davis sensor.
Davis. What's special about that?
A Davis sensor captures both traditional grayscale frames and event data simultaneously, from the same sensor chip.
Oh, interesting. So you get both types of data perfectly aligned in time and space.
Exactly. And DDD-17 has recordings from real-world highway and city driving scenarios, and it even includes vehicle data like speed and steering angle, so it's quite comprehensive.
Okay, so researchers have a good foundation of data to build upon, but it seems like the ultimate solution for autonomous driving won't rely on just one type of sensor, right? It's always about fusion. How do event cameras fit into that broader multi-sensor approach?
That's a really insightful point, and you're absolutely right. The general consensus is that sensor fusion, combining and integrating data from multiple types of sensors, is the most robust path forward for autonomous driving.
Makes sense. Redundancy and complementary strengths.
Exactly. Event cameras bring unique strengths, like their high dynamic range and low latency. Traditional cameras excel at providing rich color information and texture details. LiDAR and radar, of course, provide crucial data about the distance and speed of objects and work well in different weather conditions.
Right. They all have pros and cons.
They do. These sensors are very much complementary, each filling in the gaps of the others. One particularly interesting concept is using the fast, event-driven information from event cameras to actually trigger the capture of frames and other sensors, like a traditional camera.
Oh, okay. So the event camera says, hey, something important just happened over here, and tells the other camera, quick, take a picture now.
Sort of, yeah. This could lead to more efficient hybrid systems that aren't constantly overwhelmed with processing full frames from multiple cameras all the time. Use the events to guide the more data-intensive sensors.
That makes perfect sense, using the rapid, change-focused data to guide the slower, but maybe more information-rich, frame-based sensors. Our sources also mention a specific method for sensor fusion that's showing a lot of promise, right? DAGR.
Yes, DAGR, which stands for Deep Asynchronous GNN. GNN is Graph Neural Network.
Okay, Deep Asynchronous Graph Neural Network.
All right, there's a method specifically designed to process event data by representing it as spatiotemporal graphs.
Graphs, like nodes and connections.
Exactly. Nodes representing locations or features,
Right.
and edges representing relationships over space and time. It's engineered for both efficiency and low latency. And what's particularly exciting is its ability to effectively fuse event data with information from traditional image cameras.
How does it work, basically?
Well, DAG constructs a graph based on the incoming stream of events. It assigns features to the nodes and edges of this graph, capturing the event properties, and then it uses a detection mechanism inspired by the YOLO-X object detection model, which is a popular model for regular images to identify objects within this graph structure.
And the asynchronous part of the name is critical, I guess, given the nature of event data.
Absolutely.
Huh.
That's key. DAG employs asynchronous update propagation. When a new event arrives, it doesn't require reprocessing the entire graph from scratch, which would be slow. Instead, it intelligently updates only the relevant parts of the graph, the nodes and edges affected by the new event. This targeted updating leads to significant gains in computational efficiency.
So it only computes what's necessary based on the incoming changes.
Precisely. And research has shown that a hybrid system using both an event camera and a standard image camera processed by DAG can achieve accuracy and bandwidth efficiency that is competitive with, or even superior to, using just high frame rate traditional cameras, especially for detecting things that happen between the frames of the standard camera.
That's a compelling argument for the power of this kind of hybrid approach. It really underscores that it's not about one sensor replacing all others, but about strategically combining their strengths.
Exactly the point.
Our sources also point to specific players in the automotive industry who are really starting to embrace this technology.
Yes, they mention Japanese car manufacturers and Tier 1 automotive suppliers. They're highlighted as being particularly well positioned to be leaders in adopting event camera technology.
Why them specifically, do you think?
Well, the sources suggest it's likely driven by their strong, long-standing emphasis on safety and a culture of technological innovation. They're often early adopters of tech that promises safety improvements.
Makes sense.
And companies like Prophecy are mentioned as being at the forefront with their MetaVision technology. It's already finding its way into various automotive applications.
Like what?
For example, their tech is being used in advanced driver monitoring systems. These can detect subtle indicators of driver fatigue or distraction, like rapid eye movement, saccades, or micro-expressions on the face.
Even in low light, that's often a challenge for driver monitoring.
Yes, the sources emphasize the better low-light performance compared to traditional cameras, which is a big advantage inside a car cabin at night. This promises significant advancements in both in-cabin safety and maybe even new kinds of driver experiences.
And it's not limited to just keeping an eye on the driver, is it? Also looking outwards.
Not at all. Metavision is also being integrated into advanced driver assistance systems. There's VoxelFlow, a technology developed by Teranet AB in collaboration with Mercedes-Benz.
Ah, Mercedes-Benz involved too.
Yes, it utilizes processes sensors to achieve rapid and accurate understanding of the vehicle's surroundings. The idea is to enhance the capabilities of the existing sensor suite radar, LiDAR, traditional cameras,
Okay.
particularly in that critical 30 to 40 meter range ahead of the car, where many potential accidents occur and quick reactions are vital.
So it's adding another layer of fast-reacting perception right where it's needed most.
That seems to be the goal. It clearly indicates a growing trend towards incorporating event-based vision to create more reliable and safer autonomous and driver assistance systems.
So to bring it all together, it sounds like event-based neuromorphic vision isn't just a fascinating niche technology, but a real potential game changer for the future of automotive applications.
Absolutely. I think
Yeah.
that's a fair summary. The combination of high dynamic range, exceptional low light performance, high speed detection and tracking capabilities, that incredibly low latency, and the potential for highly efficient sensor fusion.
Mm,
It all makes event cameras a very compelling technology for the autonomous vehicle landscape.
yeah.
They offer a fundamentally different way of perceiving and interpreting the environment, which, as we've discussed, has the potential to overcome many of the inherent limitations of traditional cameras, especially in dynamic situations.
It truly feels like we're on the cusp of a significant shift in how autonomous systems see. So here's a final thought for you, our listener. Given these rapid advancements in event camera technology, how might they fundamentally reshape not only the way autonomous vehicles perceive their surroundings, but also how we as humans interact with and perhaps trust these vehicles in the future?
That's a good question.
And looking beyond self-driving cars, what other unexpected and innovative applications might emerge from this fascinating bio-inspired approach to vision? We encourage you to explore the source materials we've discussed today and delve even deeper into the ever-evolving world of neuromorphic vision.